Thank you very much, Angela, for the kind introduction. Thank you also very much, MCQST team, for organizing this wonderful conference and also for giving me this nice opportunity here to present some of our most recent research results. So actually, I already started working on those concepts about 2 or 3 years ago, and then over the time, more and more collaborators and students joined these collaborations, and just recently, we managed to finalize some of those projects, so it's actually quite good timing. So let us take a very general perspective on interacting quantum many-body systems. So here you can see n interacting electrons in some external potential energy landscape. And one of the key questions we can ask is, what is actually the ground state energy of such a system? We do not want to answer this question only for one system, but we would like to answer it in the most systematic way for an entire class of systems, namely for all those systems that we care about. So I would say in general, there are like 2 main routes for systematically addressing this electron correlation problem. So one is functional theory, and the other one is a wave function based methods. So let me describe these 2 methods briefly from a conceptual point of view. So in wave function based methods, we just minimize, according to the Rayleigh-Ritz variational principle, the energy expectation value of our system with Hamiltonian H hat over all quantum states, all n-firming quantum states psi n, to obtain the ground state energy E. And the general point is that all these wave function based methods were actually kind of designed in such a way that you could apply them, at least in principle, to every Hermitian operator on the exponentially large n-firming Hilbert space. Of course, there's some method like base or matrix product states, which then fail for specific Hamiltonians. Nevertheless, the method itself is typically applied to each Hamiltonian separately. And then if you perform several such calculations, each calculation is independent problem for each Hamiltonian H hat separately. And in some sense, by developing methods which are applicable to any Hermitian matrix on the n-firming Hilbert space, you kind of choose a route which is not particularly economical. So it's kind of an overkill. And this is actually exactly the opposite in functional theories. In functional theories, the very first step is to identify the class of Hamiltonians of interest. So for instance, in quantum chemistry, one restricts to Coulomb interacting systems. So you fix a pair interaction W, the Coulomb interaction, illustrated here in this cartoon. And then one would like to solve the ground state problem in the most concise and most economic way for only those Hamiltonians of interest. So only for those lying on this blue hyperplane, characterized by a fixed pair interaction W, and then some variable terms, for instance, the one particle potential or even the kinetic energy. So while on the level of the energy, this means to obtain the ground state energy E for only those systems which are of interest to our scientific community. So again, in quantum chemistry, it means Coulomb interacting systems. The field of ultra-cold gases means those interacting with delta function interaction. And in quantum matter physics, systems on a lattice with Hubbard on-site interaction. So then, the one particle Hamiltonians, the energy effect can be described in an exact way. And then you just need to add so-called universal function, which depends only on the fixed pair interaction W. And here now you can see why such functional theories are so economic, because here in a very first step, the entire scientific community can contribute to approximating this universal function, which depends only on W. And then only in a second step, after having obtained such a good functional approximation, one can then address the ground state problem for the entire family of Hamiltonians of interest along this blue line here, by minimizing over a much smaller space of, let's say, particle densities or one particle reduced density matrices. And it's actually the decision of the scientific community to decide how large this blue class should be and how it's characterized by a fixed W. For instance, you could fix the pair interaction and consider all possible one particle Hamiltonians H hat comprising of the kinetic energy operator and external potential energy. In that case, the natural variable, the conjugate variable, is the one particle reduced density matrix. But you could also keep the coupling constant and also the kinetic energy fixed, and then just vary the external potential So in that case, the conjugate variable would be the particle density, and this will then lead to density functional theory. So there are many different versions of functional theories that one can consider. So you can ask now, does there really exist such a universal function for every functional theory? Does it even make sense? Where does it come from? And after all, how is all of this related to the Pauli exclusion principle, which I mentioned in the title of my presentation? So let me explain this by sharing with you a very beautiful and very simple concept, namely the Levy-Leib constraint search formalism, a universal concept which plays a fundamentally important role in functional theories. So for this, let's take now our class of Hamiltonians of interest characterized by a fixed pair interaction W. And now we consider a variable one-particle Hamiltonian H hat containing the information about kinetic energy and external potential energy. To obtain now the corresponding ground state energy for every one-particle Hamiltonian H hat, at least in principle, we would need to minimize this energy expectation value over the set of all n fermion pure quantum states. So now let's try to understand how we can exploit this structural simplification of this manifold of relevant Hamiltonians. Well, for this, we keep in mind the one-particle Hamiltonian H hat is variable and the W is fixed. Therefore, it's actually rather natural to split this entire minimization process into two steps. In the first one, we minimize over those n fermion quantum states which are mapping to a given one-particle reduced density matrix gamma hat, and then only in the second step we optimize over all possible one-particle density matrices gamma hat. So, well, you can directly see where this will lead to. So you split the energy expectation value with respect to the sum into two terms, and the first one simplifies drastically. It namely reduces to a one-particle expression. It's just like the trace over the one-particle Hilbert space, the one-particle Hamiltonian, and the one-particle reduced density matrix. And the second term, we just copy it, okay? This can be arbitrarily complicated. But now the crucial simplification is that the inner minimization does refer only to the second term, so we can pull it over and obtain the standard expression of functional theories. So to obtain the ground state energy, we just need to minimize the energy function, which consists of two terms, the exact one-particle term, a linear function, and the universal interaction function, which depends only on the pair interaction W. Then you minimize this over all gamma hats. Okay, this will lead in that sense to the so-called one-particle reduced density matrix function theory, or in short, RDMFT. Let me actually summarize this even in a more general way. You can kind of say, whenever there exists a variational principle for calculating some energy expectation values, plus some structure of your manifold of Hamiltonians of interest, then via this Levy-Leib constraint search formalism, you automatically obtain a function theory. But how about the domain now of this function? Well, let's again have a brief look at this Levy-Leib constraint search formalism. This universal function f is defined only on the space of those one-particle reduced density matrices gamma hat, which emerge through this map here from one specific n fermion density operator gamma n hat. So the original way how this constraint search formalism was implemented was by restricting to pure states. So you apply the Rayleigh-Ritz variational principle to only pure states on the n particle level. This is illustrated in this cartoon here. Here you see the entire state manifold of quantum states, and the pure states psi n, they lie on the boundary, in particular the extremal points. So now we are asking about the domain of this corresponding function. So we need to map all these pure states to our one particle level, to the one particle reduced density matrix level. And then after all, it's not very difficult to see that the orientation of the eigenstates of the one particle reduced density matrix is not relevant because there's a unitary equivalence or invariance. So we just care about the eigenvalues lambda I of the one particle reduced density matrix, the so-called vector of natural occupation numbers. And as it is shown here in this cartoon, the map, all these pure states are mapped into the Pauli hypercube, but not every occupation number vector respecting the Pauli principle is mathematically possible. As a matter of fact, this horrible, complicated, non-convex blue polytope is described by extremely complicated generalized Pauli constraints. And these constraints are unfortunately so complicated but when calculate them in practice only for systems up to 5 electrons and 5 or 6 orbitals. So from a practical point of view, this functional theory for ground states in this form is unfeasible. But thanks to Steve Wallone's work in 1980, this was changed in the following manner. So Wallone observed that when you apply this variational principle, you don't need to restrict to pure states only on the n particle level. You can allow for all ensemble states. From a geometric point of view, you can say we consider the convex hull of all the pure states. This is illustrated in this cartoon here. We take the entire ball or disk. Well, again, the question is, how does the set of one-particle density matrices look like? Well, it's not difficult to understand that by considering the convex hull here on the n particle level, because of the linearity of the partial trace, you obtain here also the convex hull on the one particle level. And this domain here is now given by the Pauli exclusion principle. So if you apply this convex relaxation from here to the right side, the domain of the universal function will relax to those one RDMs which are described by the simple Pauli exclusion principle constraint. And this was actually the starting point of ground state reduced density matrix function theory. Because if you don't know the domain, you can never construct functional approximations. But here we definitely know the domain because the Pauli principle is simple. What's also remarkable here is the Pauli principle in some sense is form invariant, is form independent of the particle number and the dimension of the one particle Hilbert space. In contrast to the generalized Pauli constraints. So let me briefly tell you like the outline of the remaining part of my presentation. So these are our research results. In the first part, I'm going to explain to you how we can generalize this RDMFT from ground states to excited states. So for this, we essentially need to discuss a variational principle for this. And then in the second step, we have to discuss again the domain of this universal function that will emerge. And we will see that we're going to face the same type of problems as in ground state function theory. Then we apply this beautiful idea of convex relaxation to relax the domain. And this will then lead to a very simple generalization of Pauli's famous exclusion principle. So from pure states to mixed quantum states. And then I'm going to calculate those constraints and I would like to explain them to you and also their potential relevance beyond functional theories. So, well, how do we establish a functional theory for excited states? Well, as we discussed a few minutes ago, we just need to find essentially a variational principle for calculating excited state energies. So let me explain to you that such a principle exists. So let's take just some Hermitian operator, or you can also call it Hamiltonian H hat, and we would like to minimize this energy expectation value of this Hamiltonian over some Hilbert space, over some state space of density operators gamma hat. Well, let's first do it on the state manifold of pure states. Well, in that case, as we all know, this leads to the ground state energy E1. Okay, here's the spectrum of the Hamiltonian, and you can see indeed like all the weight lies on the ground state energy level. Okay. Well, but this can be now generalized. We can now also calculate through a variational principle the average of the lowest two eigenenergies of the Hamiltonian. I mean, for this, we don't minimize over the pure states, but we minimize over those specific quantum states with a spectrum given by 1/2, 1/2. So these are mixed quantum states with a fixed spectrum. So you have only two finite eigenstates that contribute. So in this cartoon here, the radius of this state manifold is smaller because in this cartoon here, on the boundary, you have the pure states with spectrum 1, 0, 0, 0, and so on. And the more you move towards the middle, the higher the degree of mixedness of your density operator. And exactly in the center of this disk is the maximally mixed quantum state, which is essentially the identity matrix up to normalization. And if you actually minimize now respect to the state manifold, you get exactly what you expect, namely equal superposition of the lowest two energies. Of course, you can now generalize this. For instance, if you want to obtain the equal superposition, the average of the lowest three eigenenergies of your Hamiltonian, you just minimize over even a circle of smaller radius, namely the one characterized by the spectrum 1/3, 1/3, 1/3. And of course, now given this kind of illustration here, it's not difficult for you to see that this can be even generalized to arbitrary number of eigenstates and arbitrary weights. This is then the so-called Gauge variation principle due to Gross, Oliveira, and Cohn from 1988. So here you consider just some energy levels, E1, E2, E3, and so on. And then you choose some arbitrary weights, W1, W2, W3, ordered decreasingly. And now we are interested in calculating the energy expectation value or the energy average of the EJs with the weights WJ. Okay. And this is kind of denoted here in a compact form by EW. So just imagine you had access to this EW for all choices of W. Of course, then you could extract information about the entire excitation spectrum. And now the statement is that this target function here can be calculated through a variational principle. Namely, you need to minimize your energy expectation value of the system of n fermions with Hamiltonian H hat exactly over the manifold of those ensemble n fermion density operators that have a spectrum W. So this is our variational principle for calculating specific averages of different energies. Now you plug this into the Levi-Leib constraint search formalism, and this will lead in a direct manner to a functional theory for calculating excited state energies. Namely, we call this like W ensemble RDMFT. So this in particular means via the Levi-Leib constraint search formalism, we obtain a universal function, at least in principle, is then denoted by F index W of the one RDM gamma hat. Okay. So it's important to notice that you first choose the W's, the weights, and after having made the choice, you obtain a function theory. So for each W, you obtain a separate function theory. And again, here we need to wonder, how does actually the domain of this function look like? From a mathematical point of view, it's well defined, of course, because the domain is just given by the following consideration. Consider the manifold of all n-fermion ensemble states with spectrum W, then map this manifold to the one particle level by tracing out all except one fermion, normalize it to the particle number, and this is the domain of the function. But actually, can we describe this domain? Well, obviously, the answer is no, because one special case of this W RDMFT is given by W equal to 1, 0, 0, 0. This is ground state function theory. There, you again obtain here for an arbitrary W this circle of all the quantum states with spectrum W. If you map this again to the one particle picture, you obtain again such a horrible non-convex polytope described by some generalized Pauli constraints that cannot be calculated in practice for realistic system sizes. So here it was then our key idea to apply this entire formalism, the convex relaxation again. This means take on the n particle level the convex hull, consider all points inside of this disk, and then when you map this then to the one particle level, you obtain again the convex hull of these complicated polytopes, and then instead you will obtain a very beautiful, simple convex polytope that actually then at the end can be calculated very easily. So here on the left-hand side, you obtain an unfeasible functional theory, and after applying the convex relaxation, you turn this into a practically feasible functional theory. Feasible in the sense that we at least know the domain, and I will show to you how the domain looks like now. So the goal is now to initiate this functional theory for excited states to find a nice compact description of the functional domain. And here it's actually important to understand that we are not interested in a vertex representation of this polytope, but in a hyperplane representation, because when you implement such a functional theory in a computer and run it, the minimization process of a function, you need to check the membership problem in an efficient way. So I give you an occupation number vector, and you would like to check efficiently whether you're inside of the polytope or outside. And this can be done only in a hyperplane representation, but not in a vertex representation. But let's first discuss the vertex representation, because this is more straightforward. So there's a nice duality principle which allows us to access the vertices of this polytope. So the idea is take on this polytope an arbitrary linear function, okay, which means pick a one particle Hamiltonian H hat and minimize it over this polytope. And when you minimize it, you will obtain a point on the boundary because the function is linear. So this is also illustrated here. So here you see the hyperplanes. So each hyperplane is characterized by all those one particle reduced density matrices gamma hat with a fixed value for this function here, for this linear form. And then you just need to shift now such a hyperplane of constant value along the direction of minus h hat until you reach the boundary. Okay, so notice here that this trace formula, this takes the form of an inner product, the Hilbert-Schmidt inner product on the space of Hermitian matrices. And in that sense, this gives rise to a notion of geometry. This is the reason I'm talking here about walking in the direction of minus h hat, and the hyperplane is perpendicular to it. And if you now execute this for every possible direction minus h hat, you obtain all the vertices of this polytope, and that way a nice vertex representation of this green polytope. So a priori, you can say this is a purely mathematical problem that we are addressing here, calculating a vertex representation of a polytope. But the nice point is we can interpret this as a physical problem, because here we're talking about one particle Hamiltonians or one particle Hermitian operators to be minimized over the one particle space. But we can lift this now to the n particle level, interpret this again, this h hat as a one particle Hamiltonian, and the little gamma hat is lifted to the n particle density matrix level. So in that case, we can say that this mathematical problem of interest is identical to understanding the excitation spectrum of non-interacting fermionic quantum systems. And this is actually relatively easy to solve. So this means we can, with not too much effort, we will succeed in obtaining a vertex representation of this polytope. And then with a lot of mathematical effort the last 2 years, we developed an entire mathematical theory to also turn this vertex representation into a hyperplane representation. And instead of bothering you now with the fancy mathematics, I would just like to show to you the hyperplane representation, which is nothing else than a generalization of Pauli's principle. So there is a hierarchy. So this hierarchy of exclusion principle constraints refers to the number of finite weights. It's a hierarchy in the number of finite weights. So for only one finite weight, which means W1 equal 1, which means pure states on the n particle level, you just recover the well-known Pauli principle. So let me explain again what this means here. So the lambda j's are the eigenvalues, the natural occupation numbers of the one particle reduced density matrix, which we arrange for the sake of simplicity in a decreasing order indicated by this arrow here. So here you see indeed the largest occupation number is smaller or equal to 1, which is the Pauli principle. Now let's go to the next level of this hierarchy. So to start, let's study the case of two finite weights. This would correspond to a functional theory for targeting ground state gaps, so the lowest two energy levels. In that case, the corresponding polytope depends on the W's. It's first of all described by the Pauli exclusion principle, but you also obtain a second constraint. And the second constraint takes the following form. The largest n occupation numbers are smaller or equal to, the sum of them is smaller or equal to n-1 plus W1. So this is more restrictive than what you would conclude from the Pauli exclusion principle applied to each occupation number separately. So well, if you then go to three finite weights, it's a functional theory for targeting the lowest two excited states, okay? Then you obtain a polytope described by three inequalities, the previous two plus a third one. Well, how about arbitrary number of finite weights? Well, this is of course getting more and more complicated. So the more weights you take into account, the more complicated it gets. So here in this work, it is a really mathematical work, a very long one, 60 pages. We develop entire mathematical formalism and we explain how to systematically calculate this hierarchy of exclusion principle constraints. And now I just would like to present to you the scaling behavior of the number of inequalities. So here R is the number of finite weights. The first three cases, 1, 2, and 3 is what I already presented to you on the previous slide, okay? But now here we go beyond, like 4 finite weights, 5, 6, 7, 8, 9, 10. We can even go significantly beyond 9. And we calculated all these inequalities. And here you see for the first three R values as already presented, you have only 1, 2, and 3 inequalities. And then the number of inequalities always increases. And for each level, for instance, for 7, you obtain the previous 13 inequalities plus 10 new inequalities. So the polytope is always getting smaller the larger R becomes. Okay. And there's actually one important insight here, which I also would like to mention. I like a really fundamental theorem which we managed to prove, that these generalized exclusion principle constraints, these inequalities, are de facto form independent of the particle number n and the dimension d of the underlying one particle Hilbert space. So this means that we could execute the infinite or complete basis set limit without having to calculate more complicated constraints. So this is exactly the same as for the Pauli exclusion principle. The Pauli exclusion principle is independent of the number of fermions and independent of the number of orbitals that you take into account. Quite in contrast to the generalized Pauli constraints calculated by Klyachko, they heavily depend on the particle number n and d. Here, our constraints can therefore be calculated in a very small system. Let's say you pick a fixed r equals 3 or 4 or 5 or 10 or 20. Then you pick a small system size of just 2 or 3 fermions in 6 orbitals or 20 orbitals. You calculate your inequalities, and then you can translate these inequalities into a setting of 1 billion fermions in an infinite dimensional one-particle Hilbert space. So let me briefly summarize this. So we resorted to the Gogh variation principle, used this in the context of the constraint search formalism to establish a W RDMFT, which then can be used for calculating excitation energies of interacting quantum many-body systems in an exact manner. Of course, initially there were some obstacles. Of course, the domain of the function was too complicated, but to simplify this, we applied an exact convex relaxation scheme, which actually then turned this unfeasible version of W RDMFT into a feasible one, because the domain became much simpler and we could calculate even this domain. And in that context, we revealed the existence of a complete hierarchy of exclusion principles. The lowest level of this hierarchy was just the famous Pauli exclusion principle, and we now managed to obtain all the other exclusion principle constraints for excited states, for mixed states, which means beyond ground state, pure state level. Maybe what's also interesting for you to know is that the same story is also true, also applies to bosonic quantum systems. We could repeat all these steps for bosons. You obtain a functional theory for bosons, and you also actually obtain a hierarchy of exclusion principle constraints for bosons, which is remarkable because when you study ground states, pure state for bosons, there are no constraints of occupation numbers because complete Bose-Einstein condensation is possible for pure states. But when you consider mixed states, this changes drastically. You may now wonder, okay, how about the universal function? Yes, that's true. That's the most important challenge, to find the function. So far, we have some first ideas how to approximate the function, but it's worth recalling that in a functional theory, it's a long-term endeavor for the entire scientific community around the world to approximate the function and to test different approximations. The last 2 or 3 minutes, I would like to briefly tell you a little bit more about the quantum information direction. So why are these constraints on occupation numbers relevant for quantum information sciences and for foundations of quantum physics beyond functional theory? So I give you just some ideas. This is work in progress. Just to recall the general scheme. So here we have the n particle level, n particle density matrices, and the 1 particle level. So this could be like fermionic systems, this could be bosonic systems, but it could be also quantum information systems like qubits, like n qubits or n distinguishable particles. All these polytopes also emerge in that context. So here, when we consider pure states are quantum states with a 0 degree of mixedness. So we can map this to the 1 particle picture, then we get these horrible inequalities on the occupation numbers, okay, and this non-convex polytope. If we convex relax it, we get the convex hulls. Now let's consider quantum states which are not pure anymore, but with fixed spectrum, shown in red here. If you map it to the 1 particle level, again, you get this polytope. Take the convex hull, you get the convex hull in the 1 particle picture. And then you can also consider states with very high degree of mixedness, with many contributions from different pure states. And then you get a smaller polytope. So the key insight is the higher the degree of mixedness, the smaller the corresponding polytope in which the occupation number vector has to live. This is the key insight. So let's try to use it. So the general idea is take a physical system of interest, sigma, with many particles or qubits, whatever. Measure the occupation number vector, lambda. And now the insight is the following. The mixedness of your quantum state, rho sigma, provides highly non-trivial constraints on the possible range in which you can find the occupation number vector. The higher the degree of mixedness of sigma, of rho sigma, the smaller the polytope in which the lambda vector lives. And then are very natural applications. And then you can ask, where does mixedness come from in nature? Well, there are 2 types of main perspectives. Like you could take your physical system, couple it to a heat bath at a fixed temperature T, allow for thermal contact. Then you get a Gibbs state for your system sigma, which has them some degree of mixedness because of the temperature. So the higher the temperature of your system, the higher the degree of mixedness, and the smaller the polytope in which the occupation number vector has to live. This leads to a new concept which we propose, and the concept of thermal polytopes, which would allow people or scientists in practice, by measuring occupation numbers, to provide upper bounds on the maximum possible temperature that a system can have. You can also apply it in a different context. Instead of considering temperature, you can couple your system to a second system, the so-called environment, allow for interaction, and then this also causes mixedness. So you can apply this in a static context. Just take the ground state of the overall system, you get the ground state, then reduce out the environment, get a mixed reduced state for your system sigma, and then you measure occupation numbers, and of course these occupation numbers will be fractional. But there are actually two reasons why they can be fractional. One is because of the interaction with the environment, and the second reason is because of the interaction among the particles in your system sigma. So in that sense, you can introduce the concept of interaction or correlation polytopes, which would allow one to dissect correlation between particles into thermal contribution and interaction contribution. And you can also do it on a dynamical level. Just couple your system of interest with the environment. Then not only the occupation numbers will depend on the time, but also the polytope itself. So this could lead to fruitful applications in the context of thermalization. So thank you very much for your attention.
Great, thank you very much, Christian, for this very interesting talk. So we have time for some questions, and it seems that there are some questions on Slack, in particular related to this condition that you were mentioning to be corresponding to the Pauli principle, this W1 being smaller than or equal to 1. So Jan von Delft is asking, how does that statement translate to the fact that there cannot be two particles in the same quantum state?
So these quantities, these lambda j's, which I maybe didn't define rigorously, so these are just like the occupation numbers of some very specific one particle states of your system, the natural orbitals. And these quantities are just like the expectation value, like the lambda 1 is, for instance, like the expectation value of the particle number in the orbital 1 of a system. So since this quantity is more or equal to 1, in average, you cannot find more than one particle. But now it turns out when you allow or when you enforce some degree of mixedness on the total level, it's not possible anymore to have even like one particle in the first few orbitals. And the reason for this is, just imagine you have a system and you measure occupation numbers and all of them are identical to 1 and 0. Then you can actually recover uniquely the corresponding quantum state. It's a single state determinant because you have to distribute your n fermions into n different one particle orbitals to obtain n times the occupation number 1. But the single state determinant is automatically a pure state, so it cannot be a mixed state. So this is actually, by the way, the reason why enforcing some degree of mixedness enforces some degree of mixedness of the occupation numbers.
Okay, I see. And there's another question. So could you please provide an example for a non-trivial interacting system for which you have applied your formalism to specifically compute excited states?
So, okay, I'm not sure whether I fully understand the question, but to apply it in practice, like the functional theory itself, you need to find the universal function as well. So here, we just ask the fundamental question, what's the domain in which the function lives? This is also very important because if you don't know the domain, you can even not start approximating functions. But now, to use this in practice, you also need to find a function approximation to the universal function. And this means pick your interaction of interest, let's say Coulomb interaction in chemistry. This is W, and then you need to find approximations to the function. And only then, after having found a good approximation, then you can take your function plus the exact one particle terms, and then minimizes all this polytope to obtain the corresponding energy EW. But there are some ideas how one can approximate such functions. So like one can, for instance, try to copy the ideas from ground state functional theory in RDMFT. So the first idea was there to use the Hartree-Fock ansatz. This introduces a so-called Hartree-Fock function. And then one can kind of understand some specific aspects of density matrices to tweak the Hartree-Fock function to recover quantum correlations. And we believe at the moment that we can copy all these steps also on the excited state level, at least for the case of the first two eigenstates to calculate ground state energies. But this is a really huge challenge for the entire scientific community to obtain a functional approximation, and only then can calculate concrete numbers. Maybe one last comment, which is maybe quite appealing, is One could naively try to use the ground state function that people already approximated and use in this context. So naively one would say this is complete nonsense because the ground state function is related to ground state. But here the funny point is when you target mixed states, like calculate excited state energies, these polytopes are getting smaller. So one can actually say, at least for non-interacting systems, all the information about excited state energies is encoded in the boundary of our polytopes. And this is still approximately true for weakly correlated systems. Therefore, it would be actually a cool idea, this is also what we're trying to work out at the moment, to use ground state functions, restrict them to the smaller polytopes corresponding to finite W weights, and then test this as an excited state function.
Great. So thank you very much again. And well, of course, thank you. Thanks to both the authors of this session, both the speakers of this session. Now we are going to move to the roundtable discussion. So please, if you want to keep asking any of the speakers some questions, you can just go to the roundtable using the button in any of the platforms that is provided. And let me also remind you that after this roundtable discussion, like at 4, we will have the topic tables on some very interesting topics for all of us. So please, if you want to join them, just do that from 4 to 4:30. Thank you.